Hello everyone, welcome to the GATE NPTEL lecture course. Today maybe some of you not available since GATE exam is over. So I'm just covering this topic because it's important from interview perspective. So whenever you go for an interview after your exam, this question always going to ask to you to draw a black body radiation curve for a particular temperature, how it is going to vary with an area and all that type of question. So it's an important topic, and maybe you have learned this for the GATE exam as well. So it's a part of thermodynamics course. So let's start with this. So what is black body? So black body is some kind of object which can absorb the radiations and emit the radiations. For example, if there is some sunlight that is acting on you and your body start heating, that means your body is absorbing the radiations. And if you observe in infrared camera, you can see that it also radiates the radiation in infrared. So your body is also a black body as well. And there are some kind of body which are completely black. In that sense, it will just absorb the energy. It will not radiate much. And this kind of body, even if radiate, it is outside of visible range. So this is what black body is. And radiation is a way through which the body is radiating energy. It's a way of transferring the energy. Generally, the energy is transferred in the form of electromagnetic wave, like either it is radiating invisible if they are fluorescent particles, or they may be radiating in radio wave, ultraviolet, or X-rays. So radiation is a way to transfer that energy. So when bodies are heated, they emit energy, and the way they will transfer is mostly electromagnetic waves, and that bodies are known as black bodies radiation. And that radiation is a function of temperature of your body. There are certain quantity that we are going to use in future as well. So it's better to understand this quantity. One is the total energy density. Energy density means you have energy per unit volume, and total energy density means you have taken care of all the wavelength as well. So total energy is the radiation at any point is the total radiant energy per unit volume on that point for all the wavelength taken together. And this is expressed in joule per meter cube. So if you have energy per unit volume and you have taken all the wavelength at a particular point, then it is known as the total energy density. Spectral energy density means you have energy per unit volume per unit wavelength. So this spectral energy density is defined by U lambda. Emissivity power is the power which is energy per unit time which is emitted per surface area of the body within a unit length is known as the emissive power. So you have energy per unit time per unit surface area kind of intensity within a unit wavelength range. Absorbing power, it is defined in terms of ratio. So the absorbing power of a body at a particular temperature for a particular wavelength is defined as the ratio of the energy which is radiated per unit surface area per unit time to the total energy incident on the same area of the body in unit time within a unit wavelength range. And it is defined by E lambda. So a black hole is perfectly black if it absorbs all the heat radiation it is incident on it. Whatever the temperature it is just going to absorb all the radiation. Our body are not perfectly black because we cannot absorb all the type of radiation. It is start doing some kind of reactions or maybe we start heating. So the body which absorb all the radiations, whatever the wavelength incident on it, this is known as the black body. On thermal equilibrium, it will on if your black body is in thermal equilibrium with the outside temperature, then it will also start radiating that wavelength, and they are independent of the nature of the substance. For example, if I have one body and another body, both are at 300 Kelvin. If one is form of metal, another one is another metal, but they are of same temperature. Then they will emit the same radiation. So the radiation is a function of temperature independent of what kind of body is it. So, for example, there is a spectrum of light from radio waves to microwave, infrared, visible. Visible spectrum is very narrow spectrum in which our eye also operates, and we can only see only that much spectrum. Then there are ultraviolet, gamma, and X-rays. They are high energy or low wavelength radiations. So when a body absorbs the radiation, it can emit in any of these electromagnetic spectrum. It depends on what kind of temperature the body is. So there is an experiment which is done by the two scientists to investigate how this radiation wavelength depend on their temperature or how the radiation energy depend on temperatures. So what would they is they kind of changing the black body temperature continuously. For example, here is the body's place, and they try to see how the radiation is going to be occur as a different wavelengths. Since at that time there is no spectrograph, so they have built the spectrograph by placing a prism, and the radiations from the body is passing through the slit to the mirror, and then it is going to the prism. And as you know, if it is in visible spectrum, it will going to disperse in seven colors, and if it is another spectrum, it is kind of not visible to eye, and then all this radiation is collected using galvanometer onto a screen. And so what they have found is as the temperature, the energy is going to form that kind of curve. And to explain this curve, what there are certain observations have been made. First is that energy is not uniformly distributed as a function of radiation spectrum. For example, if this temperature, the energy distribution is different compared to this temperature and this temperature. So the distributions of energy is not constant function of temperature. Now, at a given temperature, the intensity is increased. If we increase the wavelength, it reaches to a maximum and then it will again start decreasing. So, intensity curve is like that. It is increasing initially, it reaches a maximum and then it will start decreasing. An increase in temperature causes a decrease in wavelength. So, if we are kind of kept on increasing our temperature, our wavelength is kind of maximum wavelength is going towards the lower wavelength region. And what they have found is lambda m into t is constant, and this is known as also wind displacement net with the constant values given by this wind displacement constant. So maximum value of lambda is into t is kind of constant, and this is known as wind displacement law. An increase in temperature causes an increase in emissions for all the wavelengths. So if we kept off increasing temperature, that means the emission will be from all the wavelengths continuously. And the area under this curve is represent the total energy emitted by the body at that temperature for this wavelength length considered. So this is represent the total energy of your body, the area inside it. And area increases as a function of temperature with the power 4, and this is known as Stephen's law. So these are the observations that is made from this single curve. So in interview, you may ask to draw the curve, and then they will change any of these parameter. For example, they will ask you if you change wavelength, how the curve is going to behave. If you change temperature, how the curve is going to behave. What is the function on the left side? So if you remember what is this curve is, you can draw it easily in your exam. So now we have asked a very simple question. If we take this curve, we know that the energy under this area of the curve is constant. And if we kept on taking this small sample of this energy, what is the smallest area of this curve, which is kind of give the smallest unit of energy to us. So we have to find out that the smallest area, the smallest value of energy that we can get. And to calculate this value, we have done the one dimension case here. We consider that there is a box inside this area, and since the wave is emitted in the form of electromagnetic radiation, So we have formed a wave since, and we have considered that the box have a kind of reflecting ball, so it's a cavity, and now it is kind of reflecting from both the sides. So there is kind of forming a standing wave inside this cavity, the wave that is emitted. And as you know, the wavelength of the standing wave for it is given by 12 by n, where n is the number of nodes that are going to form in these standing waves, and 12 is the total length. And the corresponding frequency nu is given by c by lambda, can be written as nc by 12. And wave number k is given by 2 pi by lambda, which is n by 12. So these are the certain initial conditions, and we have to find out what is that smallest unit of energy below which we cannot disintegrate in. Now, since and for 3D case, we have axis kx, ky. For one dimension, we have k. For three dimension, we have three axes kx, ky, kz, and they are forming a kind of sphere in that 3D sphere with a radius k, which is related to kx, ky, kz by this relation. And by putting the value of kx, nx, ny, and z, we can find out the value of this radius. So radius is given by 12 nu by c. So this is the sphere in n-dimensional space. Now, if you look at the 2D case, the same problem, we have a circle and we have to calculate how many modes are there within that small area. And we can only take a value of n which are positive. So only 1/4 of that area will contain our modes. So total area will become 1/4 of the area of the circle. Similarly, if we take our sphere, then all nx and y and z has to be greater than 0. So in that case, 1/8 part of our sphere will contain our mode. So total number of mode is then given by 1 by 8 into this volume of sphere. Total number of nodes is given by 1 by 8 of what is the number of nodes inside this sphere. And we know that it is given by these expressions for 0.5 by 3 r cube. R is the radius of that sphere. From that, we will calculate the number of modes within the frequency range d nu. And by putting the value of L cube equals to volume V, we can calculate number of modes within frequency d nu is given by this range. We also add the two polarization modes of these vibrations. So this will give you 8 times. So if we change it nu by c by lambda, we will get the same expression in terms of wavelength. So according to equipartition's energy, each degree of freedom will carry an energy kpt, and if we have a number of nodes, each node will carry an each degree of freedom. That means each node carry an energy of kpt, and for n nodes within a frequency of unit range, we have n times kbt energy. So number of modes within a frequency range d nu is given by this. So multiplied by kbt is the total energy within our d nu range. And if we plot d nu versus nu, this is the kind of expression we will got. This is the known as Rayleigh-Jean's law, and it is going to show how, as a function of frequency, we are getting more and more energy. But as you can see, it is not matching with the one which is observed in the experiment. It is just an approximation version of it. So to correct this observation, what Planck has done is, instead of exchanging energy, instead of exchanging energy in terms of kBt, which says that one each node has an energy kBt, what he said is energy is discretized. It is not continuous. Since temperature is continuous, so initial hypothesis says that at each temperature we have energy, but Planck says that no, it not every temperature we have energy. We have energy only in discrete unit. So energy is not like continuous, it is like discrete. So each discrete quanta has an energy h nu, and this quanta is known as quantum. So instead of taking kBt as our energy unit, they are taking h nu as an energy unit in each degree of freedom. And since n is the total number of these Planck's quantums within an energy E, so energy in one Planck's quantum is given by total energy divided by and total number of quantums. So if n0 and 1 and they are different quantums, each carries an energy E1 into En. Then according to Maxwell distribution, number of oscillators in nth energy state is given by this expression. And as we change our energy, it, our n value will get changed. So we, at different energy level, we get different number of quantums. It's like we have a box. Instead of having standing nodes, we are having small boxes, and each box carry energy h nu. And some box may have energy 2h nu, another may have 3h nu. So they call this as number of oscillator n1, n2, n3, and they have different kind of energy. And based on how many total number of oscillator we have, we can calculate the total energy as well. And here you can see that number of oscillator is given by n1, n2, n3. And by putting the Maxwell distribution slope and applying the geometric progression sum, we get the number of distributions. Here x is h nu by kbt. And total number of oscillator is given by summation over E energy EI NI. That will give you total energy. If energy of one oscillator is E1 at one number of oscillator and two number of oscillator carry energy E2, so total energy will be E1 multiplied by N1 plus E2 multiplied by N2. This is what we have done here. Ground state does not carry an energy, so this will become En, and N can then by putting x is equal to h nu by kbt, solving the polynomial expressions, we will get the energy expressions. So energy in per node is given by, if we divide this expression by n. So this is the average energy in each node. This is how Planck constant calculate the energy. Average energy in each node. So instead of having the continuous energy kbt, now the energy is discretized by these expressions. And since total number of nodes in the volume range is given by this expression as we have calculated earlier, so energy is given by energy in one node divided by total number multiplied by total number of mode. And this then turn out to be the energy expression, and it is valid very well with the experimental observations. So by changing the hypothesis of open energy that it carry an energy of quantum h nu to an energy kb from kbt to h nu, we are able to exactly match our expressions for the energy what we have observed in the experiment. So problem with the Rayleigh's law was that if we kept on increasing nu, then it will at nu tending to infinity, energy will tending to infinity as well. But this is not happening in original situation. If we take nu to be tending to infinity, our energy is kind of tending zero. So to correct this, we have created this expression of Planck's constant. So if you remember these expressions, you can throw it even in your interview as well. So there are several questions that was asked in GATE exams. What is the total power emitted by a spherical black body of radius r at temperature T is P1, and let P2 be the total power emitted by another spherical body with half of the radius which is kept at to the temperature. What is the ratio of their power? Power is given by energy per unit time, and since energy is directly proportional to T to the power 4 within an area A, that we have seen from this plot that energy per unit area is kind of constant and is directly proportional to T to the power 4. So by from this expression, power is given by the proportional to A T to the power 4. And if we take the ratio of P1 by P2, area means pi r square. So we have r1 square here and r2 square here. By placing R2 as R by 2 and temperature T2 as 2T, we will get the ratio P1 by P2. Similarly, two solid sphere of having same emissivity, The radius of A is 4 times the radius of B. Okay. So Ra is 4 times Rb. The temperature of A is twice the temperature of B. T is twice of 2B. What is the ratio of rate of heat exchange from A to that from B? So ratio of heat exchange. So basically they are talking about how much energy per unit time you are exchanging. They are talking about the power again, and it is proportional to the area into T to the power 4. And if we multiply area into T to the power 4, we will get this expression. So that was the important question. It's a conceptual question that will be asked if during an interview. If Planck constant was zero, now it has a value of 6.623 10 raised to power minus 34 joule second. If it does not have that value, it is zero, then the total energy contained in the box will be the radiation of all frequency pole B. So what will be the energy in that case? Is it zero? It says Planck constant zero, and Planck hypothesis says that energy should be h nu, and now you put h equals to zero, but your temperature is finite. So does your energy is zero? Is it infinite as shown by Rayleigh's law? Is it 3 by 2 kBT, which is the degree of freedom, or is it kBT? That question asked in GATE 2013, and it's a really conceptual question. And the answer is if your Planck constant was zero, even though your formula says that energy is equals to h nu, however, the system will start behaving like classical system and its energy will be kBT. kBT is the energy, ground state energy of any system, classically. Quantum mechanically, it is h nu. We haven't found the formula to connect these two yet, but this is how these systems are. Okay, so I'm hoping that you will solve the problem asking GATE exam in your interview based on this topic. So prepare well. Thank you.